and you can start.
Okay, thank you. So thank you very much, Martin, for the invitation to speak. It's very kind. So there's the title. I won't say it out loud, but there's a little bit of background to this, which I haven't put on the slides, but which I've just noted down on my desk here. So there's quite a long history to non-uniqueness. It goes back to Fritz Jonin in the early 70s, and you may know that he thought that if you took an annulus and you twisted the outer boundary an integer number of times, let's say, relative to the relative to the inner one, then you could this could be a mechanism for generating non-uniqueness, or at least non-unique solutions, let's say, or minimizers in an incompressible setting. So the boundary condition in that case was ostensibly the identity. So it was a pure displacement boundary condition. And the intuition, or at least the description, was later made rigorous by Post and Sivallaganathan in the late 90s. So maybe that's only a small sample of the results that are available. So that's two papers. Another paper I'd just like to mention is the recent work of Morris and Tahiri, which is in some way connected with what I'm going to talk about today. So there they look at uniqueness or non-uniqueness in homotopy classes of maps, again on an annulus. In the context of a domain that is more like a ball, as it were, the results of Spadaro certainly have to be mentioned at this point. So he answered an open, or at least a question that was posed by John Ball in his famous Some Open Problems paper, and he showed that there are examples of strictly polyconvex functions that have non-unique minimizers. Again, it's a pure displacement type, like today's examples will be, but the difference is that in Spadaro's examples, the minimizers take on, well, at least have negative Jacobians in an essential way. And that contrasts with ours, which are completely incompressible. And so their Jacobian is equal to 1, in fact, everywhere in our case. Okay, so that's a small distinction, but the question of non-uniqueness really was settled by Spadaro in 2009. Incompressible problems have also been studied, and some results are available. The question that we pose, and I suppose must have been at the back of John Ball's mind when he sort of asked this years ago, was if we impose incompressibility, are there instances of variational problems whose minimizers are then necessarily singular in some sense? He asked that question with a Dirichlet energy in mind and with a double covering boundary condition, so pure displacement type. And the suggestion was that perhaps the double covering map itself was a minimizer. It's certainly a stationary point, and there are some results in that direction, but it's still open as far as I know. So that's the sort of setting for the problem I'm going to talk about today. We're looking at non-uniqueness in a class of incompressible variational problems. So the following is really a description without too much painful detail of a detailed study of an example. So the aim is today to show you the existence and to explain the properties of certain twist map stationary points of the energy that I've written there. I hope that's visible. And maybe if I make it a bit bigger. Okay, so there's the energy. It is d subscript epsilon v, and epsilon is a real parameter. It's greater or equal to 1. And the visible maps for this particular energy functional belong to the class script A, which is written there. So it's the set of maps in H1 on the ball, which is the unit ball in R2 into R2. So it's a planar problem. And we require that all admissible maps obey the identity, agree with the identity on the boundary, and are incompressible. Density V equals 1 almost everywhere. And we look for specific types of solutions. So the ansatz is that they are twist maps. So these are maps of the form v tilde, which you can see on the screen there, and they're given by a rotation that depends on some function k, which in turn depends only on the radius, that's mod x, and the rotation acts on x. So the rotation is standard notation, and I've written below what rotation alpha means. And you can find these mentioned in the work of Tahiri, certainly, in '09, and also that of Sivallaganathan and Spector in 2010. So I don't lay claim to having invented these maps, but they do have some very useful properties, and you'll see what they are later on. But in a cartoon sort of description, these twist maps take circles to circles, so the green circle will just be mapped to itself, but with the difference that the red point is just shifted around by an amount that depends on how far you are from the origin, and the same thing happens to any point on the green circle, so it's just rotated. Same for a yellow circle. Okay, but you can rotate them by differing amounts according to how far you are from the origin. So in this context, so with twist maps in mind and that particular energy, we find the following. So the first finding is that if the parameter epsilon is big enough, if it's bigger than √2, then the energy has infinitely many pairs of equal energy stationary points. I'll describe later what I mean by stationary point precisely, that are in the form of twist maps. So the notation is that V superscript epsilon, then plus minus, comma j. So j is an index which you can think of as characterizing the number of buckles, as I sort of hinted at in the abstract for this talk. And each such map is characterized by an appropriate k, so k epsilon j on the right here, and with either a plus orientation or a minus orientation. And you can see further down the page what happens. So these maps have equal energy. So for any given epsilon and j, if you fix epsilon and j, and you just compare the energies of, say, V plus and V minus, you find that they're the same. And moreover, you find that, that the gradients of these maps obey the following conditions, so that the gradient at the origin, which exists in the classical sense, is either plus j or minus j. So it's either a rotation pi/2 clockwise or pi/2 anti-clockwise, according to whether it's minus or plus. So in this, again, another cartoon, but it's just showing you what happens to a sector inside the ball B on the left there. So the sector gets mapped to this twisted sort of curvy red shape, and which way you twist depends on whether you have a minus or a plus. So they have equal area, so the same area, but one gets twisted one way and one gets twisted the other, and it just looked like a buckle. So we tend to call these things buckling maps. I don't claim that they have, mechanical properties of buckling and things like that. It just seems to be how they respond to being made stationary, just within the class of stationary, within the class of twist maps. Okay, so that's the opening claim. So later I will show you the remaining points 2, 3, and 4. So point 2 is fairly generic, so that these maps happen to be measure preserving, and because of the properties of the k that get associated with each of them, you find that they're C1 and homeomorphisms. So they're very nice stationary points. They're well behaved, and as is natural, when you study the maps in the incompressible setting, it's natural to look for pressures or sort of Lagrange multipliers, because the constraint is pointwise. We expect pointwise function as a Lagrange multiplier, and we can find them explicitly in terms of k, and they obey the equation that I've written with a sort of orange arrow next to it. So that if you're familiar with this arrow, you would expect such an equation to hold, and so this merely confirms that it does, although it is a bit fiddly to prove it. And the pressures themselves, they are smooth away from the origin, and they obey this sort of logarithmic um, behavior. They have a logarithmic behavior in a neighborhood of the origin. And again, that's something which crops up regularly in planar problems of this type, and I'll come back to that later. Finally, something which is at least in accordance with intuition, which is that the larger the index J, and in J in some sense records the sort of the sign changes in K, if you like. The larger this index, the more buckling you get. So although a largely numerical result, you can still express it in a sort of cartoon form by showing that it's showing the effect of a map, say V epsilon plus 2 on a sector, and you get a couple of undulations shown on the right in that picture there. Although I must say it is strictly a cartoon, because what really happens is that the double buckling goes on in a very, very small neighborhood of the origin, and you have to really blow up to see what goes on. I have an image to show you later to explain that better. Okay, so that's largely the outline of the talk. Excuse me. One final point, which if I've got time, I'll show you, is that if the parameter epsilon is less equal to √2, then the only twist map solution you can find is the identity. And in fact, it turns out that the identity is then a global minimizer of the energy d epsilon when epsilon's in that range. And that's a result that features in the PhD thesis of Marcel Dengler, who's my recent PhD student. So I shall try and explain the way he did that. It's a nice use of a pressure term in connection with these functionals. Okay. That should be D. Okay, so that's d epsilon. That's a functional. It's the same function I wrote down earlier. So let me call the integrand of that thing in the usual way, wx f epsilon semicolon epsilon. I'll gradually throw away bits of notation as we go along, but strictly speaking, it does depend on those things, and epsilon is a parameter. You are likely to ask, where does it come from? And there are two answers to that question, and there's the honest answer, and then there's the retrofitted one. The honest answer is that I bumped into it completely by accident, and it's a happy accident because I made a mistake in a different calculation and ended up studying this problem. But it turned out to be interesting in its own right, so I don't regret it. The retrofitted answer is that one can view W epsilon as a perturbation of the standard Dirichlet term mod f squared as follows. So you write f as in a particular way. That's all these steps are about. So if you like seeing the details, then the details are there for you. But the main trick, well, there are two tricks really. The main trick is to write the identity in a certain way. So here we write the identity as this expression that I'm just underlining, which is it's well known that you can do this, but it's helpful to do it at this point. And then you just expand, and you use the fact that if you look at this term here with F transpose J in it, you can pre-multiply by J, that's because J is an isometry, and you can create the term, the adjugate of F, which is cofactor transposed. And so that is how you can arrive at a particular representation at this stage just of mod F squared. So mod F squared can be represented in this admittedly complicated way. The reason I pointed that out is that if you then substitute epsilon equals 1 into the equation with a little orange arrow next to it, you find that you recover exactly that condition, and then you can trace your way back and say, okay, so W1 is just the Dirichlet energy. Okay, so then the argument is that W epsilon is a smooth perturbation of the Dirichlet energy, smooth in terms of epsilon. Although, of course, what we've done is introduce a discontinuity, which I'll come to just now. Okay, so that's the origin of W epsilon. It was a bit of luck or bad luck, or whatever kind of luck you want to think of it as. We can think of it as a perturbation of the Dirichlet energy, and the properties are as follows. Okay, so the first thing to note is that extremely important is that if x is not 0, then f going to W epsilon xf is strongly convex. And that's important throughout the work. Gives you existence essentially. And the second point to note is that we've introduced zero homogeneity. Provided f is not 0, then the function x goes to W epsilon of x is zero homogeneous, and there's no continuous extension to the ball. So it's discontinuous in x. Okay, but looking on the bright side, a consequence of the first property there, of the convexity, is that d epsilon is convex on the class script A, and it's well known that A is weakly closed. You can find that in lots of papers. So we're at liberty to apply the direct method, and this tells us that there is a global minimizer of d epsilon in that class A. So what the talk's about is an attempt to characterize the global minimizer by asking whether they might be twist maps. Okay, and it turns out you can go some way towards that goal. Okay. So my next section is twist maps as stationary points. It turns out that twist maps have a really nice property, which is that if you can differentiate them, if you choose k so that they're weakly differentiable, then automatically the Jacobian is equal to 1 almost everywhere. And so this gives you a degree of freedom. You can choose k within reason, provided it's weakly differentiable, and still remain in the class of twist maps whose Jacobian is equal to 1. So providing you have the right boundary condition, you can also infer that these maps belong to script A, the class of admissibles. So the idea is to start off with, to restrict the energy d epsilon to twist maps, and then to minimize amongst these k's. That's essentially it. So if you put v tilde as described into d epsilon, and you normalize a little bit, you find that you end up with a new functional, which I call e epsilon, okay? And it's given by that expression on the right. And okay, so it's a fairly orthodox functional. It's got it just requires a bit of extra work in order to use the direct method. That's all, because of this, essentially because of this term r cubed in front of the k prime squared there. But it's convex in k primed and it has good features. So to study this, we minimize it over k belonging to a class curly C, and I've described curly C here. So it's the set of maps in W11 on Naught 1, for which you have r to the half k in L2 and r to the 3/2 k primed in L2, and k1 equals 0. And the boundary condition there on k1 equals 0 just ensures that when mod x equals 1, that the rotation k of r is just the rotation by 0 radians, so that you're not changing anything. So you do obey the boundary condition, provided k1 equals 0. Your twist map will be the identity on the boundary of B, provided k1 equals 0. Okay, so it turns out that if K belongs to C, C happens to be weakly closed, then if K belongs to C, then the associated twist map is admissible. It's in script A. Okay, so I'm not going to give all the details of this part because it's fairly orthodox, but I will mention that there's a nice Poincare inequality which you can prove from first principles if you want to, and it says that in short that you can control the RK squared term with the R cubed K prime squared term, and that in turn tells you that this object here, norm K squared, which I've just defined here, that is a norm on C. You need the boundary condition for that, but essentially that is a norm. And that's useful when you're trying to deduce some sort of compactness from an infamizing sequence. So the goal is to minimize, or at least make stationary, E epsilon. So here is the energy E epsilon, and I'd like to make this stationary. In order to do that, I'd like to apply the direct method. And it turns out that E epsilon is SWLSC with respect to the convergences that I've written down there, the ones that you'd expect to come out. Certain changes of variables are required, but this is essentially the three things that you need. So once you've gone through this process, then the convexity in K prime squared plus the direct method gives you that there is a minimizer. And this in turn allows you to establish that that the minimizing K is smooth on the open interval 0, 1. So that's what I've indicated here. K is C0, C infinity 0, 0, 1. It obeys the boundary condition, and moreover, an Euler-Lagrange equation holds on the open interval 0, 1. So this is all sort of available essentially classically in if you apply standard theory. What's missing is that we now have a map K defined on 0, 1, and we've got one boundary condition. So it's appropriate to look for the other one, and that's where the natural boundary condition comes in. So the natural boundary condition is that R cubed K prime tends to 0, as R tends to 0 plus. And those conditions, so K1 equals 0, the natural boundary condition, plus the Euler-Lagrange equation should allow you in principle to solve for K. And we're interested now in understanding the solution of the structure, the structure of the solution set as defined. Okay, well, there's a trick, which is to turn this system into an autonomous one, well known. So you change variables and you let R be e to the t. So R goes from 0 to 1. So in order that this corresponds to the physical problem, then t should go from minus infinity to 0. And then you change to x of t given by k of e to the t. And if you do all this, then you find that a new system pops out, and the ODE that governs that system on minus infinity 0 is autonomous, and that's extremely useful. The boundary conditions also change or transfer, but they are perfectly manageable. So we write the system in the traditional way as x dot equals f of x, where x is a vector, say x, y, and f is given by that expression there. It just comes from rewriting it in a standard way. And then we look for solutions in this context instead. So the aim now is to try to solve the problem marked with an orange star. And it's natural to use a phase playing method for this. So if we try and do that, then the first thing you do is look for rest points, and it turns out that the only rest points that exist are of this form. So they are at k pi by 2, where k is an integer. And it turns out that the solutions to star, that autonomous system, are heteroclinic orbits connecting either x minus 1 to x0, or by symmetry x1 to x0. So in this again cartoonish sort of picture, the red lines represent heteroclinics, and the arrows to show the time increasing in the usual way. So provided epsilon is bigger than root 2, the solution, the phase space looks like this. I guess, okay, so what's important to note about this curve, if I just focus to start with on phi plus r, which is the uppermost red curve to start with, in order to satisfy one of the boundary conditions, which was that little x0 equals 0, you have to ensure that this heteroclinic crosses the y-axis. Otherwise, you can't ever hit x 0 equals 0 in finite time. So you can shift time because of the autonomous nature of the system, but at some finite time, you have to cross the y-axis. So if you do that at say time t equals 0, you can just rescale. If you cross the axis at say time t equals 0, and then you restrict to the green curve, which is this phi plus, but running from minus infinity to 0, well, that is a realization of the solution to star. Well, that's one realization of the solution to star. So in the case that epsilon is bigger than root 2. And I think that beneath this picture, I've got some definitions. Okay, so the phi r plus is the heteroclinic as shown. And the solution to star corresponds to a restriction of that to the green curve, if you like. Okay, so that's when epsilon's bigger than root 2, and so that's when we get these buckling solutions. Otherwise, if epsilon is less equal to root 2, this is a very nice observation due to my co-author, Jonathan Dean. He realized that that any trajectory entering this little green triangle here, which I've labeled trap, any trajectory entering that triangle can never escape. And so you find in particular that that trajectories emanating from, say, x minus 1 can never cross the positive y-axis. So you can't solve the boundary condition x of 0 equals 0 unless you are identically 0. And that explains why k identically 0 is the only possible twist map solution when epsilon is less equal to root 2. Okay. So there are different behaviors according to where you are relative to root 2, and the most interesting behaviors come when you are bigger than root 2. So let me now explain a bit more about findings 1 and 4. So finding 1 was about non-uniqueness and multiple solutions and so on. So the summary so far is that in the R system, we can find solutions of the Euler-Lagrange equation, and in fact there are two solutions. There's always k plus and k minus, and that's because there's this inherent symmetry in the phase plane. So these solutions they lie either on sort of this red heteroclinic here, the phi plus, or on the red heteroclinic down here, the phi minus. And because they're related by being sort of minus one another, a direct calculation using the energy E epsilon I described earlier tells you that they have the same energy. Okay, so that was the first claim, that there are equal energy stationary points. So that's that established at this level. Other features that come from the phase plane analysis are the following two things. So this expression, the top line here in the expression is that it tells you that the heteroclinic tends to minus pi by 2, 0, or it tends to pi by 2, 0. So the top line tells you that the y coordinate tends to 0, and this bottom line tells you that the x coordinate tends to something, and that's useful for calculating the gradients at the origin. I'm trying to explain at the moment why why you get this twist either by 90 degrees clockwise or 90 degrees anti-clockwise, and you can already see this minus pi by 2 and pi by 2 coming in here. And at this end of the heteroclinic, and at this end, that corresponds to R tending to 0, because that's where t is tending to minus infinity. So it's not surprising that these behaviors correspond to different behaviors, let's say, as you approach the origin. Okay, so a direct calculation tells you what goes on at the origin. In fact, one can write down the gradients, which is what I've done here. So dphi minus or plus looks like this. It's just an expression using quantities that we're quite familiar with. So the ER theta is just x over mod x, and the E tor theta is 90-degree rotation of that, JER. So as you let R tend to 0 plus, you find that dv minus or plus converges to one of two things. It's either minus j or plus j, where j is the rotation by pi by 2 anti-clockwise. Okay, so according to which map you're studying, you either get a rotation 90 degrees anti-clockwise, which is what's shown here on this left-hand picture, v plus anti-clockwise, or you get rotation in the other direction. So that's why you get different buckling behaviors. It's exactly because of the alpha limit properties of these heteroclinics. Okay, so that's a single buckle solution. That's essentially the simplest possible solution. How do you generate solutions with more buckles? Okay, well, this is where you use the heteroclinic in all its sort of in all its glory, as it were. So we know that when epsilon's bigger than √2, if you are a point on this heteroclinic, then eventually you will spiral in to x0, which is the origin. Just by basic arguments, by linearization near the origin, one can work out what this heteroclinic is doing. And essentially, it looks like this little cartoon here. It just spirals in, and every time it crosses the y-axis, that occurs at, say, a sequence of times, such that x at the time is 0. Little x at that time is 0. And you can see that because it spirals infinitely, then there are infinitely many such times. So each time t sort of j, let's say, allows you to rescale the solution. So you can define a new solution, which I've done here, x subscript j. It's the same as the original one, but just shifted by tj. And because the system's autonomous, we recover a solution. It's still a solution. But now we have a new trajectory, and that gives rise to a new solution kj of r, let's say, which is just xj of t via the same transformation as before. So there are as many solutions as there are crossings of the y-axis. Okay. So what happens is that when as you increase j, you find that the kj's are sort of less and less monotonic, and this essentially means the number of buckles goes up. So I have a picture to show you of a numerical calculation that was done by Jonathan Dean. So let me just change. Which one do I want? So you should be able to see a figure, and it's the left-hand figure that I'd like to draw your attention to. So this is a plot of well, it's for various different values of epsilon. But if you fix on one particular epsilon and then look at the pattern that's established, as you increase j, which is increasing the number of buckles, you find that log of minus ej, which is the energy associated with it, that decreases. Now, the ej's all turn out to be negative, which is why you need to have a minus sign in front of it. But what this tells you is that as you increase j, at least numerically, you increase the energy that's associated to it for each fixed epsilon. Okay, and then as you vary epsilon, that same pattern is reproduced. So the more you buckle, at least numerically, the greater the energy cost associated with it. And now I'll just show you a quick picture of what the buckling actually looks like. So you should now be able to see figure 5, and it's a plot of the effect of the map V5 plus comma 2 applied to a sector. And what goes on is that there are 2 buckles now. That's the point of the 2 there in the definition of the map. And you can see that the buckling is sort of confined to a tiny region near the origin, and you have to really blow it up, which is what's been done here by that little box. Sort of zoom in. You have to blow it up in order to see what's going on, but essentially it's the same thing as before. You have a rotation by sort of pi/2 radians, sort of at the origin, as it were, but then you have these buckled parts further out. Okay, so that's just a brief extract of the numerics. Okay, so what we should now have is that there are infinitely many equal energy solutions, stationary points, let's say, and the bigger J, at least numerically, the greater the energetic cost, which corresponds to our intuition, at least. Okay, so the second part of the talk is about stationarity and the associated pressures. So what we're looking for is effectively the Lagrange multiplier, which satisfies this top equation here in the distributional sense. But all we have at the moment is essentially one-dimensional information about these twist maps. All we've got is the second order ODE satisfied by K plus boundary conditions. So there are 2 approaches to this. The first is to establish the existence of a pressure sort of rigorously, and that can be done. And then the second part is really to try to find it somehow. So in the following, I'm going to let capital U stand for either V plus or V minus. Okay, so the first step is to show that this equation holds here. So I want to show that I need to demonstrate that stationarity holds in this sense. So that is that the integral dw dot gradient phi composed with u vanishes under the assumption that the test function phi is divergence free. Once this has been done, you can establish using well, there's a very nice paper by Fosdick and Roya Kafani, which was written in '99. We can establish that the first step's result can then be strengthened or changed, if you like, to read the following. So it reads as follows. So one can replace 0 on the right hand side with some function, which turns out to be in L2 in this case, or in fact in all the LP spaces, multiplied by divergence phi of y. And this is true now for all phi. So we don't need the divergence-free constraint. Okay, so this is still something that has to be established. Having done that, we can then turn that expression into something which is more recognizable, which is the thing I've got one red star by further down the page. So if you use the invertibility of u, which you do have in this case, and change variables slightly, then you find that you recover the form that at least seems more familiar to me for arbitrary test functions. That's what we're trying to get to. That's what I would think of as being the pressure. And in principle, star then enables you to solve for P. So you should then be able to find the gradient of P, in fact, away from the origin according to this expression. So I've got some more comments to make on that shortly, but that is roughly speaking the idea. We go from a star to 2 stars, and given that we know what U is, we should be able to find P. And if we do that, then the result is given here explicitly in terms of K by this equation that I've marked with a yellow circle with a dot in the middle. Okay, so that is the expression for P. It's just a function of R. Okay, so that's the overall strategy. What does one do in practice, and what are the interesting points about it? Okay, well, it's just a calculation, you could say. On the other hand, there are some nice properties of these twist maps, these pairs of twist maps. So if U is V plus and say capital V is V minus for concreteness, you can see that they're inverses of one another. So the first step, which was to show that that the gradient of W dots with the gradient of phi composed with U for div free phi, that becomes something that has to be shown in terms of some other map sigma tilde that I won't write down now. It's just something you can derive from the setting. So it becomes something one has to check. But the nice thing about it is that because these two maps are self-inverse, the thing you have to check is just a problem of checking something that depends only on K. So that's why I've written sigma tilde K here. So in other words, you have to check that the curl of sigma tilde vanishes. And in practice, you find that that can be done. It turns out that if K solves the Euler-Lagrange equation, then the curl of sigma tilde does vanish. And so we can conclude from that that U is a stationary point in that full sense. So we've gone from essentially a 1D stationary point in that class C to a full stationary point in that sense in the big class A. So that's a piece of luck, or anyway, it's true. Okay, so that's the first bit. So there's a nice bit of sort of symmetry in the problem that enables you to conclude that you have a stationary point in the higher dimensional sense. So that now we can say that that star holds. Let me show you star again. So this is star with one red star. So we know that this thing holds in principle. The question is now, can we find P? So that's what double star is supposed to be doing. You can't necessarily go from star to double star, obviously, because at the moment all we know is that the P in star is an L sort of intersection. It's in the intersection of, say, the LP spaces for P bigger than 1. So that's the basis of my second comment here. So star holds for some P in the intersection of these spaces here. This doesn't necessarily say we can. This doesn't necessarily mean we can say that double star holds. However, what you can do is proceed by brute force, and you find that the left-hand side of this expression here is du transpose and so on. If you calculate that, you find that it can be written as the gradient of something that depends only on R. So that gives you a candidate for P. And then you can use the uniqueness that comes from the Royer-Cafani result to say that to within an additive constant, that is the pressure. So it's enough to find a pressure that has this behavior on balls, well, on B, but away from the origin. It's enough to have such a P, and then you can invoke uniqueness. So the only thing one has to do is to check that it's check that you've got enough control on the behavior of this gradient. So I've put in a short proof of that fact. So I claim that this particular P that I wrote down earlier has this behavior that x dot the gradient of P is bounded above by some constant, depends on epsilon. And from this, the logarithmic behavior of P itself follows. The reason I mention the proof is that it shows the use of a conservation law that is associated with that Euler-Lagrange equation, and which I haven't mentioned so far, but it turns out to be pivotal to the whole calculation. Not just this calculation, but the whole paper. Okay, so so the starting point for this thing is to write x dot gradient p. So I've already defined p, so this is just following the definition I gave. So x dot dp looks like this. So it's just a function of r and k. Okay, but effectively it's a function of r. If you remember that k is a solution of the Euler-Lagrange equation, then you can apply this conservation law, which is most easily expressed in terms of the t variables. So x of t was k of e to the t, y was x dot. And in those terms, we find that y squared can be written like this. It's just some expression, some integral expression. I defined omega earlier. That's the function with epsilon cos squared and things like that in it. So it's omega is a well-behaved smooth function. And if you use these variables, it turns out that you can write x dot p in a very neat way. You can in fact write it as the integral of something. Okay, so you're integrating a function g s comma t against something else, e to the 4s minus t, and the function g is explicitly known. It's this function here. It's I've written it here, 2 omega 1s minus and so on. So that's g. And all you need to know for g is what omega 1 and omega 2. Omega 1 is exactly omega from earlier. And omega 2 is like omega 1, except you replace epsilon with epsilon squared. And if you do that, you see that there are these bounds on the right that I've written in green. So omega 1, for example, sits between 1 over epsilon and epsilon. Here, epsilon is always bigger than 1, right? So these bounds make sense. And if you apply elementary bounds, you can bound g pointwise by that constant I mentioned earlier, which I've just called a epsilon here. Okay, the integration doesn't affect things very much. So we find that in fact x dot p is pointwise less equal to 2a epsilon, providing x is not 0. Okay, so you can see from this that p has to behave like this. So we find that p is in fact bounded by some logarithmic behavior. Mod p is smaller than, say, a epsilon log r. And that's something that comes out of the double covering problem with the Dirichlet energy. You find, in fact, for that problem, you find that p is equal to something like 3 over 2 log r. We can always find pressures in those contexts, but here it's a little bit harder because we don't know k explicitly. Okay, so the behavior of p is in some sense controllable, and that enables you to go from knowing its behavior on, say, balls bounded away from the origin, to finding the distributional form of that equation. So that's just an exercise now in the convergence theorems. Okay, so the point of this was to establish that we have some sort of control over these pressures. They are not worse than logarithmic. Now I should just to finish. How long have I got? In the last, say, 5 minutes, let me just mention this nice result which pertains to this particular problem, and this is due to Marcel Dengler, who was my PhD student until recently. And using some nice techniques which exist in the literature, he managed to prove the following. So he said that if epsilon's between 1 root 2, so this is the setting where there are no buckling maps. There are just the only twist map solution in this case is the identity. He showed that in fact the identity is the unique global minimizer of d epsilon. And to do so, he made use of the fact that when in the case of the identity, it is a stationary point, and we can write down explicitly its pressure. So the associated pressure is always minus 2 p epsilon log r, And I should say what P epsilon is. Sorry, I forgot to do that. So P epsilon is just a positive number given by that. Okay, so we know exactly what P is, and there's a really nice trick that can be used in this setting. So we want to try and understand the behavior of d epsilon for a general v that is admissible. So you write the v as identity plus something, and the something is obviously v minus identity, and then you expand it using the fact that d epsilon is effectively a quadratic functional. Okay, so then you get some extra terms, and clearly what we're trying to do is to look at these last two terms, which I'm just going to put an orange line over. So if we can take these terms and show that their sum is greater or equal to 0, then we can conclude that the identity would be a minimizer. Okay, so what do you do? Okay, well the first nice thing to do is to note that this mixed term here, the first one on the left, dw epsilon, etc., you can regard that as appearing in the Euler-Lagrange equation once you've got the pressure involved. So if you do that, then that allows you to write this term down in terms of the pressure, which is what I've done here, remembering that the stationary point is the identity. So if you do that, you get the first term is just the pressure times divergence of eta. Okay, the next nice trick is to relate div eta to det d eta, and you do that using the fact that that the map V in this setting is incompressible. So if det dv equals 1, then that tells you that there's a relation between this quadratic object det d eta and div eta. So if you do that, then you can replace div eta with det eta, and this gives you a lower bound function, which is the function I've written here. Oh, sorry, there should be an extra term on the right there. Which of course I've missed out throughout. Now the point of exchanging what is a linear term for a quadratic term is that now you have a chance of combining these first two terms. So you find that this d epsilon eta is bounded below by something that is nice and quadratic, and by using various tricks from the literature, you can bound this second term below by something that is also related to the Dirichlet energy. So the upshot is that the energy d epsilon of v is bounded below by d epsilon of the identity plus something, and the something is just a prefactor times Dirichlet energy, and you see that the prefactor is positive exactly when epsilon is less than √2. So this was Marcel's result, and it's a very nice statement because it says that the identity is the unique global minimizer when epsilon's between 1 and √2 strictly, and it's just a global minimizer if epsilon's √2. We don't know whether it's unique or not there. So my only remark to add to the tail of this nice theorem is that we know that when epsilon's bigger than √2, you have an exchange of stability. Effectively, the twist maps then have lower energy than the identity. So as you cross √2, so you swap over the possible minimizers, and this at least shows you that the twist maps have lower energy. So the identity is not a global minimizer for when epsilon's bigger than √2. Okay, so that's the end of the expository part of the talk, and let me conclude, if I may, with just 3 open questions. So the first is, what is the status of these stationary points, these buckling stationary points? Are they local minimizers in script A when epsilon's bigger than √2? That's one question. Bearing in mind that the more you buckle, the higher the energy cost. it's natural to wonder whether just the single buckling solutions are global minimizers in script A when epsilon is bigger than √2. Again, I don't know. And finally, the question that goes back to the origin of W epsilon. I mean, is this energy physical in any sense and in the incompressible setting? I don't know. But in components, in case it helps, that is an expression there for W epsilon in components where mu is the polar angle. So you can see very clearly it's not continuous. Okay, so those are my 3 open questions, and that's the end of the talk. So thanks very much for listening.
Yeah, thanks a lot, John, for your nice talk. And now I think we can come into questions. So the talk is now open for questions, remarks, and comments. So please ask if you have a question.
Go ahead.
May I?
Yeah, and maybe I